Hello YouTube, welcome to this channel. Today we will start a new chapter having the name Magnetism from the grade 9 physics. In this chapter, there are some table of contents that we are going to follow. In the first video, we will dive into some important terminologies that are related to this chapter. And then in the next videos, we will move towards few advanced topics like domain theory, magnetic field, induced magnetism, types of magnetic materials, and Earth's magnetic field. Now, before diving into the detail of magnetism, we should know that the term magnetism came from the region called Magnesia. Now, introduction to magnetism says that magnetism is a fundamental physical phenomena that arises from the interaction between magnetic field and moving charges. Now, in this whole definition, the major point that should be highlighted is that magnetism deals with the interaction of magnetic field and moving charges. Whenever there are going to be some moving charges, as a result, there is going to be a magnetic field. And the interaction between magnetic field and moving charges is what we call the magnetism. The next thing is to get to know about the types of magnets. In the chapter of magnetisms, we will be using few names of magnet. For example, we will be discussing a bar magnet that has a shape of a bar. Then we will be discussing a U-shaped magnet that has a U shape. After that, we will somehow discuss the ring magnet. Ring magnet has a circular shape in the form of a ring. And at last, we will be discussing the horseshoe magnet. The horseshoe magnet has a little deformed U shape and it looks like the shoe of a horse. After that, the important thing to know about is that what causes magnetism. Magnetism arises due to the motion of charged particles like electrons. As we have already studied that magnetism is the interaction between magnetic field and the motion of charges. So now, whenever there is going to be motion of charged particles like electron, as a result, magnetism is going to be studied in that specific system or specific phenomena. Now, discussing the motion of charged particle, motion of electron, it could be anywhere. For example, there are certain electrons moving in an atom. Those electrons are going to be as the cause of magnetism. Similarly, in case we consider the motion of electrons in a wire, that example is also going to be considered as a cause of magnetism. So it doesn't matter what the scenario or the system is. Whenever we are going to study the motion of electrons, the movement of electrons, or the movement of charges, that thing is going to create magnetism in the system. So, in this example, we can see that there are certain electrons that are revolving around the nucleus. These electrons are basically undergoing two types of motion. The first one is orbital motion, that these electrons are moving in an orbit, like in the circular form around the nucleus. Another motion these electrons are undergoing is the spin motion, that they are spinning around their own axis. So these electrons are undergoing two types of motion, and both of these motions are going to be considered as the cause of magnetism. Now moving towards the second example, when we have some free electrons, and these free electrons are moving or flowing through a circuit, or in other words, we can say that these electrons are moving through wire. So in this example, the motion of electrons in the wire is also going to be considered as the cause of magnetism. After that, there is one very crucial bullet point that we have to remember throughout this chapter, that atom is considered as a tiny magnet. Whenever we are going to use the term atom in this chapter, it means we are referring that atom as a tiny magnet. Now, bouncing back towards the same concept that we have studied in the previous slide, that we have an atom, and in this atom there are certain charged particles, there are certain electrons, and these electrons are undergoing two types of motion. The first one is orbital motion and the second one is spin motion. And both of these motions, the movement of charged particle is simply going to be considered as the cause of magnetism. So in short, we can say that electron is moving around the nucleus, and as a result, the motion of this electron is going to make this whole atom turn into a tiny magnet. So as a result, this atom is going to be equivalent to a tiny magnet having a north pole and a south pole. Now, discussing about the motions of electron. The first one was spin motion and the second one was orbital motion. Spin motion means when an object rotates around an axis through its center of mass. It means that an atom or a body is moving around its own axis. When a body rotates about its own axis, this is what we refer to as spin motion. And on the other side, the motion of an object moving around another object in space following a curved path is called an orbit. When an electron is revolving around the nucleus in a circular path, that motion is going to be considered as orbital motion. Now, we have already studied that motion of the charged particle is equivalent to the magnetism, is considered as the cause of magnetism. So this was the first type of motion which is going to be considered as the cause of magnetism, and this one is another kind of motion that is also going to be considered as the cause of magnetism. Now there is a twist in the story that the spin motion produces magnetism that is very small, and as a result we say that the spin motion produces a very small amount of magnetism. Hence, we neglect that magnetic force or magnetism that is produced by spin motion. While on the other side, the orbital motion produces magnetism that is a little noticeable, and as a result, we say that we call an atom equivalent to a magnet only because of the orbital motion, because orbital motion causes the magnetism that is noticeable, while the spin motion causes the magnetism that is negligible. Another important term to dive into within the category of magnetism is the magnetic field. Now, simply defining the term magnetic field, we can say that the region around a magnet or a current carrying wire where magnetic force can be experienced is called magnetic field. Consider this example, that in this case we have a magnet, and around this magnet there is a region, there is an area, there is a specific portion where we can see these imaginary lines. At some areas or some regions you are going to see some circular lines, and there are going to be parts where the lines are going to get extremely straight. So in this example, we can say that this is the region in which we can experience the magnetic force of a certain magnet, and as a result, this area is considered as the magnetic field of this magnet. Now, moving towards the term magnetic monopole. Magnetic monopole is basically a hypothetical particle with a single magnetic pole. Now, emphasizing on the term hypothetical particle means it is an imaginary particle that does not exist in nature. So in case someone is going to say that we have a north pole, and from that north pole there are certain magnetic field lines that are emerging out of that pole. The answer to this statement is simply going to be that magnetic monopoles are the hypothetical particle and they do not exist in nature. While on the other case, whenever we are going to consider magnetism, we are going to say that North Pole and South Pole always exist together. There is no isolated North Pole or there is no isolated south pole. Hence, magnetic monopoles do not exist in nature. Now discussing magnetic monopoles a little more in detail, we cannot say that there is an isolated or a separate north pole. Similarly, we cannot say that there is a separate south pole or an isolated south pole. When we consider the example of a north pole, we always have to remember this thing, that from north pole the magnetic field lines are emerging out, while on the other side, whenever we are going to consider a south pole, the magnetic field line is always emerging into the south pole. After discussing magnetic monopole that do not exist in nature, we move towards magnetic dipole. Dipole basically means two poles. A particle with two magnetic poles is called magnetic dipole. And magnet always exists in a dipole form. Whenever we are going to consider a magnet, one pole of that magnet is referred to as north pole, while the other side of that magnet is referred to as south pole. In case you simply try to break or separate apart these two poles, you break apart the magnet into two forms. These two forms are again going to be forms of magnet. This huge magnet is then be broken into two different other types of magnet, while making the first portion as a north pole and south pole, similarly the second portion as north pole and south pole. Hence, magnet always exists in a dipolar form. We can never separate the north pole or the south pole of a magnet. Now, when we consider the north pole and the south pole, we simply can induce a new term called magnetic dipole moment. The measure of strength and the orientation of a magnetic dipole is called magnetic dipole moment. Similarly, we can represent magnetic dipole by the symbol nu, and as a result, we can express magnetic dipole moment by these arrows, while these arrows point out from the north pole and then enter into the south pole. Now, summarizing the whole details that we have studied throughout this lecture, let us consider you have a spherical or a cylindrical body in this shape, and let's assume that this body is only made up of 3 atoms, while every single atom being a single magnet. As a result, we can replace an atom with a magnet, because we have already studied that an atom is always equivalent to a magnet, while the second atom is equivalent to second magnet, and the third atom is going to be get equivalent to the third magnet. As a result, we have the atomic figure and the magnetic figure of a specific substance. Now, we can replace the magnetic figure with a dipole figure as well, while each magnet represented by this dipole arrow. After the magnetic figure, we can draw the dipole figure of this system as well. In dipole figure, every single magnet is going to be replaced by a dipole magnetic moment, that is represented by a single arrow. In this case, we have total of 3 magnets. As a result, we replace all these magnets by using dipole magnetic moments, that are 3 arrows. This was all about today's video. In the next video, we will be covering the domain theory. Thank you so much for watching. In case of any question, feel free to ask in the comment box.